Hello everyone. Here in this video, we'll look at the piecewise linear transformation functions. So the piecewise linear transformation functions, these are defined in pieces rather than one formula here. And the principal advantage of the piecewise linear function over the other types of function is that the form of piecewise function can be arbitrarily complex, and the disadvantage is their specification will require more user input. So the types of piecewise linear transformation are contrast stretching, intensity level slicing, and bit plane slicing. So coming to the contrast stretching, it is one of the simplest piecewise linear functions, and it enhances the overall contrast by spreading the intensity levels. So the low contrast images, these can result from the poor illumination, then lack of dynamic range in the imaging sensor, and the wrong setting of a lens aperture during the image acquisition. So contrast stretching, it can be defined as a process which expands the range of intensity levels in an image so that it spans the full intensity range of the recording medium or the display device. So here you can see uh, figure is for the contrast stretching form of the transformation function. In this figure, uh, usually this figure is used for the contrast stretching, and the location of the points R1 S1 and R2 S2, it is like these two will control the shape of the transformation function. R1 S1 and R2 S2 will control the shape of the transformation function. If R1 is equal to S1 and R2 is equal to S2, then the transformation will be a linear function, and that produces no change in the intensity levels. If R1 is equal to R2 and S1 is equal to 0 and S2 is equal to L minus 1, then the transformation becomes a thresholding function which will create a binary image. Okay, so if this is the case, that is R1 is equal to S1, R2 is equal to S2, then the transformation will be linear and there will be no change in the intensity levels. If R1 is equal to R2, S1 is equal to 0 and S2 is equal to L minus 1, then this transformation, it becomes a thresholding function. It will create a binary image. Okay, and if there are intermediate values, that is intermediate values of R1 comma S1 and R2 comma S2, then it will produce various degrees of spread in the intensity levels of the output image, and thus it will affect the contrast. So again, in general, if R1 is less than or equal to R2 and S1 is less than or equal to S2, so here it is assumed that this function is a single valued function, and here it will preserve the intensity levels and prevents the creation of the artifacts in the processed image. Okay, so here if R1 is less than R2 and S1 is less than or equal to S2, so this is assumed to be a single valued and monotonically increasing. Okay, and this condition, it will preserve the intensity levels and also prevents the creation of intensity artifacts. So the transformation function stretched at the levels uh, linearly from the original image to the full range. So here the levels, these levels are stretched linearly in this range, that is 0 to L minus 1, and the contrast stretching, it can also be obtained by setting R1 comma S1 to R minimum comma 0 and R2 comma S2 to R maximum comma L minus 1, and where these R minimum and R maximum, these will denote the minimum and the maximum levels in an image respectively. So here we are taking a low contrast electron microscope image of the pollen, which is magnified 700 times. This I have taken from the textbook, and this is the result of the contrast stretching. Okay, so what it will do, the contrast stretching, what it is doing, it is enhancing the overall contrast by spreading the intensity levels here. So you can see some clearer picture, because this is, here the contrast is low, so here the contrast has been enhanced. Next is the intensity level slicing. So here in intensity level slicing, here it is highlighting a specific range of intensities in an image which is of interest. Okay, now the application include enhancing the features such as masses of water in the satellite imagery, and then enhancing flaws in X-ray images. And this process, it is often called as the intensity level slicing, which can be implemented by using two basic themes. Okay, so here the first approach is to display in one value. That is, we want to display in only one value, either black or either white. So suppose we want to display in one value in the range of interest, and here the all the values we are taking it as, suppose, white, or we can take all values in terms of black. Okay, and here this figure, it shows the transformation function which highlights the range of a comma b. Okay, here a comma b, and it will reduce all other intensity levels to a lower level. And the second approach, it is here the second approach, it is shown in this figure, where it will highlight the range of a comma b, and it will leaves other intensities unchanged. So in the second approach here, it is based on this transformation function which is shown in the figure, and here it will brighten or it will darken the desired range of intensities, and leaves all other intensity levels in the image unchanged. Okay, so you can see here this transformation, it will highlight this range and it will reduce all other intensity to a lower level. But here it will highlight this range, and it will leave this range unchanged. That is, the intensities which are in this range from A to B, these will be highlighted, whereas the other intensities other than this will be unchanged. But here the other intensities are reduced to a lower level. That is the main difference. Now again I'll take the same image. Okay, that is the image of a pollen, and here this is the result of contrast stretching which we have seen, and when you do the thresholding you will get such type of image. Okay, so what it will do, thresholding, it will convert a grayscale image into the binary. Okay, this is the grayscale image, it is converted into binary, that is black and white, and all the pixels above the threshold will be white, and below the threshold will be black. And these are used in segmentation, then object detection, document image processing, etc. And next, coming to the bit plane slicing. So here the bit plane splicing, here the pixels are digital numbers which are composed of the bits, and instead of highlighting the intensity level ranges, here we can highlight the contribution which is made to the total image appearance by the specific bits. That is, what we'll do here is, we will split the 8-bit image into 8 separate layers which are called as bit planes, and the higher bit planes, these will be having the important image details, and the lower bit planes, these will be having the fine noise and the textures. Okay, so the bit plane slicing, it peels off the image bit by bit, and it will show how much detail each bit carries. Suppose here this figure is there. Here it is an 8-bit image. It may be considered as being composed of 8 1-bit planes, Okay, here we are having bit plane 1, bit plane 2, 3, 4 and so on up to 8 bits. Bit plane 1 is the least significant and bit plane 8 is the most significant. So here uh, it is containing the lower order bit, all of pixels in the plane, and plane 8 all the highest order bits. Okay, now suppose I'll show you one figure here. This is the figure. It is a this figure it is a 8-bit grayscale image, and it is of size 550 into 1192 pixels. Now if you see these images 1 2 3 4 5 6 7 8, from here will not calculate, this will see first. This is our bit plane 1, 2, bit plane 3, bit plane 4, 5, 6 and 7. So the 4 higher order bits, bit planes, especially the last two, will contain a significant amount of visually significant data. Now if you can see from these figures, the last two bit planes, that is 7th and 8th, in this the data is visible. Okay, here the data is somewhat visible, but here the data is visible here. Okay, but in the lower order bits, these bit planes, okay, here these are having the subtle intensity details in the image. We cannot see anything here. So the decomposition of the image into the bit plane, it is useful for analyzing the relative importance of each bit in the image. And in this type of transformation, this is also useful in image compression, where the fewer than all planes are required or used in the reconstructing of the image. Now suppose these bits we don't want, so we'll not consider this. We want only, suppose, the higher level bits or the higher order bits, we'll consider only that in order to reconstruct the image. So here this bit plane slicing, it can also be used for image compression, then steganography, noise analysis. So in general, the bit plane slicing, it peels off the image bit by bit, and it shows how much detail each bit carries. Okay, so here this was about the intensity transformation functions. In the previous video we have seen about the negative log, then power law, piecewise linear and bit plane slicing. Here in this video we have seen the piecewise linear and the bit plane slicing, and these all are the powerful tools in order to enhance the image, and they improve the visibility and highlight the important details. And mastering these all intensity functions will give you the foundation for almost every advanced enhancement techniques. So I hope you have enjoyed the video. Thank you.